Okay, so we can start the next session, which is third. Actually, the chairman of this session should be Professor Romuald Tarczewski. Unfortunately, he can't be with us today because he had a contact with somebody who has COVID, and that's why he's not here. But I strongly believe he's with us online.
Yes, I am.
That's why I have to take the duties of him. So, and I would like to introduce the first lecture that will be delivered by my dear friend Igor Siotor. Igor graduated from Technical University of Wrocław, where he was a teaching assistant, and also he was a lecturer at University of Palermo, Italy. He's been principal in architecture and engineering professional practices on large projects completed in several countries on 4 continents. As architect, he has designed first built tension membrane structures in Canada, in Thailand, and in Malaysia. Since 1996, Igor has been working on the execution side of construction industry, and he has developed a specialty and the expertise in the technology of lightweight structures. He has been working with tension membrane companies in America, in Asia, and in Europe. Now he's working with a multidisciplinary firm, Pfeiffer Structure, mostly in North America, and on selected large projects. Igor has participated in the construction over 30 bridges, 40 sport facilities, mostly stadium roofs, and number of smaller jobs where cable structures, tension membrane, and retractable systems has been successfully completed. So we have a general lecture. Igor, the floor is yours.
Thank you, Professor Schaffer, for this very kind and long introduction of my entire CV. Good afternoon, ladies and gentlemen. Thank you for attending and welcome to my presentation, which is about the design, engineering, and installation of the world's largest cable net. But because the actual motto of this conference is about lightweight structures in the civil engineering, let me revisit fundamentals of what that actually means, lightweight structures. So let's start with the definitions. There are very poetic definitions developed by the architects, of course, working with the light. That comes from the architect who has actually designed and built buildings with the stone pillars and stone arches. However, he wanted to see this vision of large open spaces. You can read the other definitions. This comes from Joseph Paxton, who built Crystal Palace in 1851. He wasn't an engineer, he wasn't an architect, he was a gardener. He has designed and built the largest greenhouse in the world. Never been built before, and it was a temporary structure. Now the Chinese want to reconstruct it according to the old plans, or maybe they will. However, here is a definition by Fry Otto, which is actually very practical, how to achieve more space with less materials. The simple rule of the thumb in the construction industry is anything that is a structure with a dead load less than 55 kilograms per square meter could be considered as a lightweight structure. For comparison, you are all familiar with the Bird's Nest, which is a stadium for the 2008 Olympics in Beijing, or Peking in Polish, China. The dead load of the steel structure of the roof just is close to 900 kilograms per square meter. The designers of the stadium claim it is a lightweight structure. So go figure. A little bit of the historical events. Again, that was the theoretical paper produced by the architects in late 18th century. The first building which was built with the steel frame, was in 1877. Of course, there's the Eiffel Tower, built in for the Paris exposition. The first building which was built with cables supporting a roof was in 1933, built in Chicago. And then, of course, there's a 4-point structure designed and built by Siotor in 1955, which weighs not even 5 kilograms per square meter. So here, that was just the revisiting of what does it mean to be a lightweight structure. This presentation isn't about the cable nets. There are several types of cable nets. This is a very simple orthogonal net where two layers of cables intersect in one plane. Incidentally, if you look at this guy, he's not wearing any safety belts. This was done in the late 70s, this picture. The regulations on the construction site were a little different. Here, you see the layout of the cable net prepared on the floor, on the ground, with all the nodes intersecting, ready for the installation. The cable net, which in this case, this is an ice skating ring in Munich, in Germany. It is supported of a single arch, and it's hanging from that arch, covering the space of 100 by 90 meters. So that's one of the advantages of the cable nets. It can span large distances with minimum dead load of its own weight and provide protection from the environment. This entire building is clad with the membrane, and it resists all the loads, applied loads in Munich, which includes snow load, of course. The cable net could be formed, a similar concept of a cable net, but could be formed by boundaries of the catenary cables, which form totally different spaces. Here's Munich Olympic Stadium. That was a concept design of Siotor, but he was not the engineer of record. Engineer of record was Schleich-Bergermann. This is the same building, which is done during the construction. Initially, it was clad with plexiglass panels. What you see here, these darker lines, these are not cables. This is a joint, between the individual plexiglass panels. Now there's a polyethylene panels. The actual main supporting structure are these tiny cables with the upstands at the nodes, which support the roofing. Another example of a cable net, which forms a saddle dome, fully enclosed building. This is a velodrome for the London Olympics, completed in 2011. Again, you have the cables intersecting at the nodes. This is a picture during the installation. One other important aspect of any cable structure. Cables have to be pre-tensioned. Cables with no pre-tension forces in them have no stiffness and no stability. What's more, well, you know all of that, but what's more interesting is the higher the pre-tension in the cables or higher the forces, the tension forces in the cables, that increases the stiffness of the entire structure. To the point that in order to reduce the deflection or deformation of the entire structure, you have to increase the pre-stress in the cables. The increased pre-stress of the cables equals the higher diameter of the cables. And then it affects the economics of the project. So the design of the shape of the form of the building, of the structure, is not the only answer to create efficient, economical, lightweight structure, which is this example. Again, you see the intersecting cables with the node, which support the roofing. And here's the final building. What's interesting about this one is that It was late development. The construction was late, but the date of the Olympics was approaching, and they had to build something. They had to build this velodrome. The cable net, which was basically delivered to the site prefabricated and installed, was erected at the 1/3 of the time schedule, which was allowed for the traditional construction method, and was delivered at a half price. These are the sort of a pragmatic facts of the reality of the life in construction industry. Everything counts: time, money, and experience. Here you see the picture of the inside. You hardly see the supporting structure, which are cables. It's another example. Here you have a cable net layout in the radial arrangements. It's called bicycle wheel. It has a hub, it has the spokes, and it has a rim. In case of a stadium roof, you have a hub, you have the spokes, all working in tension, and you have a hub which works in compression. If not for the wind, that would be Tensegrity system, large-scale Tensegrity system. Unfortunately, the wind doesn't want to blow from that direction and at one speed, and it does create the reaction loads, which are other than the vertical on the system, so therefore is not purely theoretical Tensegrity system. Any applied loads, either the uplift or download, result in a different distribution of the tension loads or the tension forces in the system, and sometimes very large deformations, very large deflections. For the stadium roof of the size of, say, 50,000 seats, the deformation of this here is actually, I'll show you on another slide. Here's the system of a Kuala Lumpur National Stadium. Here's a compression ring, and here are two tension rings. This roof, there's no snow loads in Malaysia. But when the wind blows, depending on the direction, this roof deflects by 1 meter. Here's a domestic example, Śląski Stadium in Chorzów. It's also a bicycle wheel. It has two compression rings. Here's one, and here's two, and here's second. And this is a tension ring with the radial cable trusses. This is how it was built. It actually was built twice. The second time was built right, actually. And this is after construction. The radial cable net could be also a dome. Here's a BC Stadium in Vancouver, in Canada, which is designed with a retractable inside roof, which is here, which can carry the snow load. And the retractability, the mechanization works. Which brings us to the subject of this presentation, which are double layer orthogonal cable net. Why is it different? The difference is that you have the top layer of cables, double cables, lower layer of cables, intersecting cables, and the struts connecting them. Such a system has ability of carrying enormous loads of a large span. And that brings us to the subject, who is Pfeiffer? Pfeiffer is a company who actually builds these things. Pfeiffer has been building lightweight structures for 442 years. That's not a joke. And what is the stadium? The stadium has been designed to be a center of entertainment, not just the stadium. This is located in Los Angeles, arguably the center of the world center of entertainment. Hollywood is there, all sorts of the film studios, and all the artists live there. This is what the architects have envisioned that as a light structure which doesn't resemble the stadium and provides the housing for not only sports events. The entire roof I lost the control of the entire roof over the stadium covers the area of 8 hectares. So it's 300 by 2, right. This space just over the stadium, that's a copy of an architecture model as it was designed. There's also open plaza and the performance center for 6,000 people. Everything under one roof. This is the Italy architecture model. This is a structural model. And this is when our company got involved and we actually were challenged with developing something that could be built. And I'm going to challenge you a little bit. If I go back, have a look at these models. Here's the structure, very Italy structure model. Here is the analytical model that we have built, which underwent millions load cases analysis. And if you have any questions about it, I'll be happy to answer it later. And here, as a result, this is a system model, and this is so-called BIM model, well, which I have my opinions about the definition of what BIM model actually means. So my quiz to you, my challenge to you is this. Can you tell me what are the difference between this model and this model? I'll give you a little hint. Remember what I showed you about the bicycle wheel? Okay, well, I'll wait for your answers after I finish, okay? So this is what we have built, analyzed tediously. What adds to the challenge of this project is that it is clad with a single layer ETFE. ETFE is film. One of the mechanical properties, the characteristics of this film is it elongates 300% before it breaks. So if you start pulling on this film and you have 1 meter long panel, 1 by 1, before it breaks, it becomes 3 by 3 meters. So does it snow in LA? But it rains. It could be torrential rains. So when you have the roofing material, which can elongate almost endlessly before it breaks, the ponding or lack of the rainwater runoff on the roof becomes the problem, like for any tension membrane. Ponding is the big no-no in the analytical analysis or analytical modeling of any tension membrane structure, specifically the one which undergoes huge elongations. So here is our model of the ponding model of the entire roof, which led to the, whatever is red is overstressed. So which led to the revision into the entire design of the entire supporting structure, which is a cable net, which resulted in a higher pre-stress, which would reduce the deformation and deflection, which resulted in a higher tension in the cables, but it was a safe roof, which covers 8 hectares, I repeat. So, and then leads to the detailing of the actual roofing, which is the film, the ETFE system, and the detailing of the entire roof, which of course is done again on the sophisticated programs, analytical programs, which calculates hundreds or thousands of load cases. And then there's erection engineering. Designing the roof is any long span structure is producing the final picture of it. Now the erector, a company like ours, we need to figure out how to actually build it and how to install it and how to tension the cables. So here are the examples of designing the temporary structures which allow us to lift the cables and then to pin them and then to tension these strand jacks each one weighs 3 metric tons. And they create the forces of 1,000 tons each. These are the pre-stress forces which the cables on this building, on this structure required in order to be installed. The erection process starts with the laying out the entire cable net on the floor of the building. As you see, the stadium is complete, it's built. Even the windows in some of the VIP suite boxes are in place. So we pin the cables. We start with the top layer because that is there's a lower level of tension in this, in the top cable net. And then we install the lower cable net, and the final tensioning happens in the middle of the tension ring. This is this apparatus which you saw on the other picture. And here's the complete tension, completely tension cable net. Now, about the ETFE roofing system, because this building is fully enclosed, it's not a dome because it's open on both sides, but because of the natural properties of the ETFE, there was a potential of huge heat buildup underneath the roof. It's like a greenhouse effect, which of course it's not welcome, so it had to be eliminated. So the design called for the operable ETFE panels. You see the 19 by 19 meters almost individual panels. Some of them had to be operable. Here is the mock-up of individual panel. This is during the installation. And here is the mechanization of 16 of the panels, which had to open up with the ETFE on it automatically for natural ventilation, so as to prevent the heat buildup underneath the roof. And this is how it was designed and eventually installed. And here's the stadium just before the opening game. In conclusion, what I would like to add to this presentation is this. We all talking about the role of the architects, engineers as a consultants on any project, starting from a small house through to a bridge or big stadium. What I would like to point out from this presentation is that the role of the builder, executioner, the people who actually build this, can influence the design of a structure of the building, going back to the square one, to the very beginnings, and presenting the need of reconsidering or revisiting what has been assumed by the designers, by the consultants. The historical event, the example of that, and I bring up Wright again because he is a forefather of the lightweight structures. When he started doing his models, producing models on the soap bubbles, and then started drawing them by hand, there was a person, a tent maker. His name is Peter Strohmeyer in Constance, small city at the south end of Germany, on the border between Germany and Switzerland. He was actually building this. Wright could never understand how these people knew how to compensate the material. Usually it was PVC, lightweight PVC material, to allow for the pre-tensioning during the installation and fitting the space that he has designed. But he actually started working for Strohmeyer. He was working as a laborer, being already the PhD candidate. He worked in a shop on the fabrication floor, stitching the panels of PVC to understand how it works. Not to mention that Peter Strohmeyer was actually financing his structures. But this is how the fundamental understanding of the execution of the theoretical projects was developed and evolved into something that Wright could later use in his design work. So thank you for your attention. And now I would like to go back to my quiz and please tell me what are the differences between these models. Yeah. Professor Schaffler, of course, that's the right answer. What was missing here? The cable net, the top and bottom cable net, had to be, the forces in the cable net had to be resolved in the steel structure which is around. That was extremely inefficient. The steel was failing. Why? Because there was nothing which would collect all of these tension forces, resist in form of a compression, which is the hub of a bicycle wheel, and then would carry almost vertical. There is a sliding forces, unfortunately, but because of the wind, but would carry all the resulting dead load forces to the ground through the columns. That is the fundamental difference. It may sound simple and silly, but this is what basically resulted in efficiency of the structural system for the huge roof and made it buildable. Thank you.
Thank you for this extremely interesting presentation. So I strongly believe that we have a time for one question or one remark. Anybody? Okay, so Igor, once more, thank you that you came here and thank you for your presentation. Right now, I'm just giving the microphone to Professor Kamiński to lead the.
Unfortunately, I lost a single lecture because we have simultaneously PhD defense at the faculty, so it was necessary to run and to make a voting. Nevertheless, the next that is invited lecture, but by Robert Studziński from Poznań University of Technology, and this would be about sandwich panels, use of the blind rivets as sandwich panels. Dr. Studziński is assistant professor right now in Division of Structural Engineering, Faculty of Civil and Transportation Engineering of Poznań University of Technology. He's a member of Polish Association for Computational Mechanics. That is fantastic, I'm the same. Awarded by several rectors of Poznań University of Technology awards. Scientific field of interest covers design, optimization, and sensitivity analysis of sandwich panels. Usage of the blind connections with sandwich panels, failure mechanisms of sandwich panels under the static and blast loads. Design of steel structures. Author and co-author of 36 scientific publications and supervisor of 115 bachelor and master theses. You are very patient. Please.
Thank you for your kind introduction and for the invitation me to this conference. Thank you very much. The topic of the presentation is the use of the blind rivet in sandwich panels. The aim of my research was connected with the experimental studies of the use of the blind rivets in sandwich panels. The sandwich panels are composite structures which are used as wall and roof cladding elements. I assume that the blind rivets can be used to attach some building infrastructure, such as switchboards, control boxes, photovoltaic panels, sprinkler systems, and so on, to sandwich panel. And unfortunately, there are a number of variables that need to be addressed in this type of connection. And later on, I will explain which are these variables. So let's take a look about this drawing on the left side. This is the standard way of connecting infrastructural element to building facade. I mean, we use through drilling fastener, and we need to use some additional structural element. When we use blind rivet, we should be able to suspend or hang on the building infrastructure without penetrating the core layer. That we don't create point thermal bridges, and we do not need some additional structural element. So the pros and cons The pros is ease of installation, no additional supporting structure, and no point thermal bridges. The cons, there are no practical guidelines, and there are no standard regulations so far. So let's go through the scope of the laboratory tests. I considered two types of blind rivets. They are characterized by almost the same diameter, and they are all aluminum almost, but the main difference is the number of folds. Here we've got 4, there's 3. The way of installation is quite similar. The difference is with the used tools. I mean, there is a riveter. Here we've got some sleeve on drill or simply hand wrench to install this fab lock. So on the right side, we've got the blind rivet. On the left side, we've got fab lock rivets. I consider sandwich panel. The sandwich panels are composite structures which consist of 2 thin facings. Its thickness is about 0.5 millimeter. And there is a core which is made of soft but of high thermal insulation properties materials. In the research, I investigated the use of steel and laminate. I investigated 3 types of core material: pure foam, mineral wool, and styrofoam. And also I considered the lack or occurrence of primer layer. The primer layer is the layer which is applied at the external facings, while the pure foam is emerging. It improves adhesion abilities between the facing and the core. And of course, we should investigate a number of load types and load case scenarios. That's not all cases. I mean, I consider axial and eccentric load. The eccentric was assumed by this eccentricity in the laboratory tests. Nevertheless, we should also investigate shear, but so far I didn't perform tests which will show the shear response of this type of connections. And on the right side, you see the test bed arrangement. The samples were made of sandwich panels. Its width was 350 millimeters and over 250 millimeters. I assumed that the panels were fixed at both ends. And to control the deflection of the bottom line, I, during the test, considered measurement of this deflection using the load transducer. Of course, during the test, the load was controlled and the displacement of this loading cell. Okay. To summarize, this table presents the number of tests which were already performed. Each case, I mean 1 to 17, is represented by at least 3 or 4 samples. So let's take a look at this table. The red line, the red cases, covers the type of the blind rivet. Then the yellow one covers the influence of the facing material, steel versus laminate. The green one refers to the occurrence or not of the primer layer. And the last one part is related to the different load case scenarios. I mean, axial static, eccentric static, axial cyclic, eccentric cyclic, and of course, different core materials. That's the scope of the test. And let's take a look at some results. At this figure, at this slide, you see the difference in the mechanical response of the blind rivet, I mean bulb tied, with 3 folds installed in the steel facing with no primer layer and in laminate facings. So you see the level of capacity is different. The ductility of the connections is also not the same, but also there is a different failure mechanisms. In the case of bulb tied steel facing, we observe the lamination. In the case of laminate, we observed the pull-out failure of this connection. Then at this slide, you see the differences between different core layers, pure foam, mineral wool, styrofoam. And there's also presented on the left side axial pull-out, and here on the right side eccentric pull-out. And what is observed, the angle of this load path was higher for the eccentric pull-out of this blind rivets. Another example, another result, the use of different blind rivets, the fab lock, the black line, and the bulb tight, the orange line, in case of steel and laminate facing. You see also that there is in this case, the primary layer were used. So you see the different failure in opposite to this pure delamination of the facing without the primary layer. And the last part of my research was connected with the analytical models. I tried to find some correlation, and I think that I thought that I can use the simple, well-known models of beam on elastic foundation. I investigated Winkler, Vilianenko, Borodich, and Pasternak model. Of course, there are some well-known assumptions of those models. Of course, I inverted this I limited it to the point force and to the tension, not to compression. And to verify this model, these models, I performed some number of additional experiments, but this time the samples were beams. In fact, the width of this sample was not 250, but only 60 millimeters. And I tried to find that for the elastic range of the response of this connection, I will be able to correctly predict this behavior using these analytical models. So I choose 100 newtons force, and that's the result of it. I mean, this is a simple numerical model. This line refers to this 0.473 refers to the experiments, and the other lines refers to the analytical models. The results are quite close. And to conclude, the use of the primary layer increases the ductility of the blind connection. I observed that the use of 4 instead 3 clamping arms increases the stiffness of the blind connection. It was observed that the stiffness of the blind connection is the same for sandwich panels with mineral wool and expanded polystyrene cores, while in the case of pure foam core, it's lower. It was also revealed that the eccentric load, regardless of the sandwich panel core layer material, increases the stiffness of the blind connection. Quasi-cyclic load has no negative influence on the mechanical response of the blind rivets, and it was found that all presented analytical models allow for description of the elastic range of mechanical response of the pull-out test of the blind rivet from the sandwich panel. And at the end, some future outlines will need to be covered. I mean, it should be considered the determination of the shear strength of this type of connection. We should consider the cyclic tension compression load cases because it could be crucial for this type of connection. We could extend the analytical formula for 2D model for the plate. And it should be also considered the influence of the suspended load on the overall sandwich panel capacity. And thank you for attention.
Thank you very much. The paper is now open for discussion. Maybe you have any questions to the author? Any comments, maybe? Or criticism? If not, I would like to say that it is very attractive for people from reliability analysis that you provide mean values and standard deviations for material properties, because it is usually hard to find in any paper from experimental analysis area these statistical parameters, but they are necessary to provide reliability index computations. Okay, fine, thank you very much. Okay. Right now we would have a very interesting, particularly for me personally, lecture by Ileana Calotescu from Romania, I hope. Full-scale behavior of a telecommunication lattice tower under wind loading. The floor is yours.
Thank you. First of all, I would like to say that I'm very happy to be here in Poland. I took a while to decide to come, but I'm happy that I did. It seems that Polish people are very relaxed, very friendly, and I love Poland. From the 2 days I spent here, I just want to say that. I prepared this presentation related to the first wind monitoring system for a telecommunication lattice tower that was installed in Romania this year, in collaboration with Professor Maria Pia Repetto from University of Genova in Italy, and my colleague, Professor Daniel Bîtcă. My name is Ileana Calotescu. I work at the Technical University of Civil Engineering, Bucharest, at the Steel Structures Department. Which one is? Okay. Okay, can just stay here.
Wolno.
Yeah. It's always a wonder that so many complicated things can be done by researchers, but this always puts us in trouble, I think. It's okay. From my memory. The outline of my presentation is quite simple. I will present the monitoring system, all the sensors that we have installed. And then I will just show some example of data acquisition for a synoptic wind event together with some response parameters, mainly related to the accelerometers that we measured on the tower. I don't have any conclusions, but I will state them myself. So just as an overview, first of all, I have here a map of Romania. We are almost neighbors. The monitoring system is installed in the western part of Romania in a city called San Nicolau Mare. This is the coat of arms of the city, which is dedicated to Saint Nicholas. I chose this location based on the study that I did some years ago related to wind damage that occurred in Romania, that I found based on newspaper reports in mass media. And I found out that the western part of the country is the most affected by thunderstorms. I would like to mention that the main objective of this monitoring system is to measure and study thunderstorm winds in Romania, and then to study the behavior of lattice towers to this kind of winds. The thunderstorm wind loading cases is not introduced in wind loading case yet, so a lot of research is done in these in present days in order to do that. But in order to add them to the wind loading code, we first need the measurements. So this is how the location was chosen, and I have here some examples of damage that occurred in that city. Mainly, the damage is most of the damage usually happens at the roof level of small one-story, two-story buildings. Of course, we have damage also caused to trees or crops. Also, hail damage is quite important in thunderstorms. And these are just some examples of events that happened in that city. This is our tower. It is a 50-meter tall antenna tower, which is located at 1 kilometer from the city. You can see it's in open field, so it's very clear all around. We have corn in these fields, which is very helpful when we want to see the direction of wind, because you will see how the crops will deform. Let's say this tower, as I said, has 50 meters in height. All the elements are have circular hollow cross sections. Bracing patterns varies along the height. We have 10 segments, 7.5 meters at the base and 2.3 meters at the top. It's a triangular lattice tower. The geometry of this lattice tower is very common for Romania. Most of them are like that. We performed the finite element analysis of the tower in order to get the dynamic characteristics, and you can see here the first two modes of vibration are flexural modes with 1.72 hertz in frequency. Then third mode of vibration is torsional. Then again we have two modes of vibration, flexural modes, which are again coupled, and the next one is also torsional. Related to the monitoring system, first of all, I would like to speak about the entities that are involved. First and foremost, University of Genova, who supported this research. So they offered the grant, the money, in order to be able to buy all this equipment. Technical University of Civil Engineering in Bucharest, Romania, where the monitoring system is actually installed. I would like to thank Telecom Romania Communications, because the tower belongs to them and they offered for free the tower for study, to study it. And then I would like to thank the people that actually won the bid to install all the instruments, because they really did a great job. As I said, it was the first time such a complicated monitoring system was installed on a lattice tower in Romania, and they did not give up on me, although they did not make a lot of money out of this project, but I convinced them this is important. So what is the equipment that we have? First of all, ultrasonic anemometer, which is installed at the top of the tower, a temperature sensor, 2 triaxial accelerometers, 6 strain gauges, data acquisition system, of course, the server located at the university, and we also have a video surveillance system, because my dream was to see the clouds when thunderstorm happen, which actually is very helpful to decide between events. This is the geometry of the tower with the installation of each sensor. So at the top we have the anemometer and the temperature sensor. We have one accelerometer at the top, another one at about 27 meters. And all the strain gauges were installed at the bottom, 3 on the legs and 3 on the diagonals at the base. Initially, we wanted to install one strain gauge also upper at about 40 meters, but we gave up because it's too difficult. Some pictures, these are intermediate steps of installation. Ultrasonic anemometer and temperature sensor in the box, in the white box, accelerometer, which was then covered with a box in order to protect it from climate, from wind and snow. And this is a small strain gauge on one of the tower legs. This is the data logger, which is installed in the shelter located at the base of the tower, and with all the channels for each sensor. And this is the PC working station in my office in Romania, where we gather all the data, which is then weekly transferred to Genova University. This is one of the 3 or the 4 cameras. Actually, we have 3 cameras pointing towards each direction, so we cover more or less 360 degrees, and one camera pointing towards the shelter. This was for protection, because we needed to ensure this equipment, and it was a requirement. And these are some images that we can see from our surveillance system. Data acquisition is done using the IMC Studio software, which comes with a data logger, and then we have other software for data transfer and then to read the data. This is more or less how the database looks like in this step. We have 1 minute of data, which is transferred from the data logger to the computer, and then we create a 24-hour MATLAB file for each day, which looks like this. And I would like to thank Lixiao at the University of Genova for writing the script in order to get the 24-hour MATLAB files like that. So you can see measurements of wind speed and direction, and then temperature, accelerations in the middle, and strains at the base. Now I would like to present one event, but first of all, these are the characteristics that were obtained based on the Romanian wind code, with focus on the gust velocity factor, which is about 1.7 at 10 meters and about 1.54 at 60 meters. This is based on a 10 minutes average wind speed. And this is the event. So when you read about wind velocity, they always say that it's a Gaussian stationary event. Trust me, in 1 hour, almost 1 year of measurements, it's very difficult to find a Gaussian stationary event from wind velocities measured on site. But we found one on May 18th, 2021. You can see the gust factor is 1.27, so a bit smaller than the one provided in the code. We do have some other events that occurred after I wrote the abstract for this conference, for which the gust factor increases a little bit. So you can see no change in direction at all. Change in direction is sometimes representative of a thunderstorm. Average wind velocity in 10 minutes is 11.6 meters per second. And you see also the distribution, which looks very much like a Gaussian distribution. And related to the response characteristics, I'm only presenting here the acceleration data. The accelerometers are placed. I have the Y and Z directions of them. So Z direction is parallel to the face of the tower where the strain gauges are. We have two diagonals at the base, and the face where we have the two diagonals is the Z direction of the accelerometers, and then the Y is perpendicular. And you can see here that the first mode of vibration, the first frequency of vibration is really well identified from the acceleration data. The torsional one, so the third mode, we don't see a peak. I suppose the next ones may be the flexural modes of vibration. And then we have this peak around 7 hertz, which I'm not sure if it really belongs to the torsional mode or not. And here are all the other plots corresponding to the both direction for the accelerometer at 50 meters and the accelerometer at 27 meters. And they all identify these peaks. So of course, these are preliminary data. We are just now starting to study also the strain measurements and get the complete response of the tower, both for synoptic events and also for thunderstorms, which is actually the main purpose. Well, instead of conclusions, I would like to acknowledge first and foremost Professor Giovanni Solari from University of Genova, who sadly passed away last year in November, to whom I owe all my career in wind engineering. He had a love for wind engineering, and he had a love for students, and he helped everybody, all young. He loved young people a lot, and he always offered his help if he saw you needed it. So this project was researched mainly because of him, because he believed in what we can do here in Romania. So I would like to thank him. Maybe he can hear me also now. I would also like to thank Professor Maria Pia Repetto, who took over this project. And you can see in the middle picture, we took a picture together on the installation day. So we are working together on, she's coordinating this project, and we are working together on it. And like I said in the presentation before, I would also like to stress the importance of the people who are actually installing these instruments for the workers, let's say. And these are the guys that went up the tower when it was like the coldest day in January, and it started to snow. And they say that if it snowed, they would not go up the tower, but they did. So I would like to thank them for their dedication, because it was quite dangerous, but they did it. Finally, I would like to thank you all for your attention, and I would like to invite you to Romania, because next year, hopefully, we are going to host on-site the European African Conference on Wind Engineering. It was supposed to be this year, but we had to postpone it because we really wish to make it on-site. The website will be open soon, and we will start abstract submission in January. So I kindly invite you to participate to this conference, and you can come to Romania as well. Thank you so much for your attention.
Thank you very much for a very nice lecture. I think that some people should have the questions. A lot of.
Thank you. Let me ask you this. Thank you for a nice presentation. Do you have in Romania the weather phenomena which is called freezing rain? This is, no, hail is actually, it falls. Freezing rain, it's like a drizzle which freezes when it touches the surface. In this case, the tower, the steel pipes of your tower, forms the icicles, increases the surface of the resistance of the tower, and increases the deformation and the loads and the wind in geometrical order. Now that changes everything.
It's a separate loading condition where we have both wind and ice on the tower, and we do have that because in Romania we have all the seasons. The winters are very cold, the summers are very warm, so in the cold winters we do have that problem, and we need to take care of it when we design lattice towers.
One other thing I would like to add, which Professor Schaffner could verify or not, but from my readings, 75% of the failures of telecommunication towers is attributed to the ice load. Not the dead load, increased dead load, but the increased wind load because of the icing on the structural members. Questions?
First of all, thank you for great presentation, and I think that this research is just brilliant. I just love it. So I have just one question. I have a lot, but one here. Can you read the deflection of the tower and the stresses where you have the strain gauges in the context of the wind direction and the wind speed? That's possible with your equipment?
So we cannot read the deflections directly, but my colleagues from Genova University have developed a method that we intend to use it to get the deflection from the strain together with acceleration. So this is in process. Sorry? Yes, we have to calculate it. We don't get it directly, unfortunately, but this is one. Yes, this is one purpose. Now we are starting to writing the papers. We are starting to analyze the data. Until now, we waited to get the data, and fortunately, we have about at least 10 events that we can call thunderstorms. And one of them, I'm not happy, but I'm happy to say we measured 150 kilometers per hour during this summer in June. The hail produced a lot of damage to about 200 houses because we went there to do the damage survey, and we are preparing a paper on this issue. So I'm not happy for the people of San Nicolau Mare, but I'm happy for this research that we managed to get the data and get something out of it. Thank you. Thank you so much.
Just one question. Yeah. I have the question to the audience. Do we have in Poland association for wind, a Polish association for wind engineering? Yes? Yes. Okay. Thank you very much. I think, but that's the comment to the presentation. So I personally go to this conference. Nevertheless, I have a comment to your presentation. I think that better approximation of random wind would be to apply extreme values distribution, because extreme values distribution is just to model, from mathematical point of view, to model extreme phenomena. So Fisher-Tippett distribution or even generalized extreme values distribution. But Just a comment.
We are just waiting to get the date because we already in January we will have 1 year of data, but for what you mentioned, we need more years. So this is in plan. Yeah, thank you.
More towers for free. Thank you very much. Okay, we skip to the next presentation. This would be about initial prestress level on behavior of tensegrity domes. I have the name Marina Solovei. I'm not sure if this is right.
My name is Marina Solovei. I'm from Calotescu University of Technology. And today I want to present my work with Paulina Obara and Justyna Tomasik about the impact of the initial prestress level on behavior of tensegrity domes. My presentation is organized as follows. Firstly, I'm going to discuss the steel domes in general and present traditional and non-traditional domes or tensegrity domes. Then I want to describe the basic description of tensegrity structures and going to take a look at the analysis of these structures. Then I will present the examples and results that were obtained. And finally, we go on to the conclusions. So the steel domes are one of the oldest structural systems, and the traditional domes were known since 18th century. However, the non-traditional or tensegrity domes were designed only 70 years ago. The traditional steel domes can be divided into classic mesh domes, which are consisted of only one layer of rods, the multi-layer mesh domes, which consisted, as name says, of 2 or more layers of rods, and cable net domes, which consist of cables and struts. However, the cables are the main structural elements. The mesh domes can be distinguished according to the mesh type, number of layers, and type of plan. And here are presented a Schwedler dome, rib dome, and the lamella dome. And in our work, the Schwedler dome was investigated. The non-traditional or tensegrity domes were first mentioned by Fuller, and he presented the geodesic dome, the first known structure with tensegrity features. And of course, the next researchers present other works, which was based on Fuller's. And the Geiger present his structure of dome, which consists of cables and struts in the state of self-stress. The Levy, who modified Geiger dome by adding extra cables. Kevit, who was inspired by lamella lattice shell, and of course the others. Now, what is tensegrity? Tensegrity systems has a unique rod-like structure. They consist of compressed elements that are separated from each other and tensed elements that create a continuous net. These structures are in continuous state of self-stress, which reduce the infinitesimal mechanisms that also exist in these structures. And an example of tensegrity is a work of Kenneth Nelson, Needle Tower. Tensegrity structures has 6 characteristic features that are listed on the slide. And according to that features, the structures can be classified as ideal tensegrity, pure tensegrity, structures with tensegrity features of class 1 and 2, and beside of the other classification, the first 3 classes are characterized by the mechanism, the infinitesimal mechanism, while the last one is not. complete analysis of Tensegrity structures, it is a two-stage process. And the first stage is qualitative analysis, which can be done through the singular value decomposition of the compatibility matrix B. And according to this analysis, the self-stress states and mechanisms are terminated. And then the classification of the structure can be also described. And the second stage is quantitative analysis, which can be done through the quasi-linear theory or second-order theory and third-order theory. And according to that, the S-min and S-max values are terminated, and also the impact of the self-stress on the displacements, the load-bearing capacity, and the global stiffness of the structure is considered. So in our work, the next structures were analyzed. The Schwedler single-layer dome, which consists of only the struts. The modified Geiger dome, which had 6 load-bearing girders and had an additional cables, horizontal, and original Levy dome, which consists of consists of 6 load-bearing girders, and the cables create a triangular net. And all 3 domes were 20 meters wide and 3.5 meters high, measuring from the supports, of course. The results. During the analysis, 2 types of loads were described. I'm sorry. During the qualitative analysis, the self-stress states and mechanisms were discovered in Geiger dome, and this classify this dome as a structure with tensegrity features of class 1. However, in Levy dome was no mechanism, so this classify this dome as a structure with tensegrity features of class 2. And the single-layer dome or Schwedler dome has no tensegrity features, so cannot be considered by this analysis. Here are presented a normalized superposition of self-stress states for Geiger dome and Levy dome. And the forces in the elements were normalized in that way that the maximum force in the struts were -1. And here we can see 2 types of loads that were analyzed, the asymmetric and symmetrical. And here shown an impact of Prestress level on displacement Qx for Geiger dome for both load types according to the second-order theory and third-order theory. And as we can see, at a low level of the self-stress, the second-order theory was insufficient. However, with an increase of the self-stress, the results for second and third-order theories were comparable, almost the same, for Geiger dome, of course. For Levy dome, the same analysis was performed, and we can see the results that self-stress states, the level of self-stress state does not affect on the displacement according to the second-order theory and the third-order theory. It's constant all the way. And for the single-layer dome, the same analysis was performed, and the displacement of the node was comparable to the Levy dome, as shown in the pictures. Here is shown here we can see a load-bearing capacity for the Geiger dome and for the Levy dome. And we can see that the increase is almost linear with an increase of the self-stress state. However, for the single-layer dome, it is constant. And in the case of the global stiffness parameter, it's still linear, almost linear for the Geiger dome, but it is constant for the Levy dome. The single-layer dome was not considered in this parameter. According to the conclusions, I would to summarize the main points of the presentation. So, the self-stress impact on the each parameter, static parameter of the Geiger dome, only impact on the load-bearing capacity of the levy dome, and the single layer dome is not considered because has no self-stress. And in the end, we can compare the behavior of the each dome according to the displacement, when we can see the large displacement for Geiger dome and small for the levy and single layer. The impact of the load, where the Geiger dome is sensitive for the load and the two other is no. And the impact of the self-stress level on the Tensegrity domes, which is high for the Geiger dome. And in the conclusion, that shows that the level of the self-stress impact on the structure, on the Tensegrity structure, only if this structure has a mechanism, infinitesimal mechanism as well, because otherwise this impact is minimal. So we can say that in our work, the best dome was the Geiger dome because it was able to control the static parameters of this dome, which is better and useful in the designing of the structure. Okay, and this is the end of my presentation. Thank you.
Thank you very much for your presentation. Do you have any questions to our presentation? If not, I would like to ask about the software and computer model. What was the software name? And
then we have the script. It was a Mathematica environment, and there was the script programmed, and we just input the data, like the nodes that we have, and the Mathematica showed us all the results.
this was some finite element method software, or in Mathematica some code? And okay, and what type of the finite elements? Or just degrees of freedom into the node?
Elements, degrees of freedom, number of elements, number of nodes, and also, no, that's all.
Thank you very much once more. In this session, we have the last presentation. I remember that about 20 years ago, everything was better with wavelets. So right now, there was a time of nanomechanics, but before nanomechanics, there was mechanics with wavelets. So a lot of problems is still open in this area. And my colleague, Michał Guminiak from Poznań University of Technology would like to present some analysis that is an application of the discrete wavelet transform to damage detection in flat truss girders. Please, Michael, the floor is yours.
Thank you, Mr. Chairman. And thank you, Mr. Chairman, ladies and gentlemen. And I would like to say that it is the privilege that I am here on this conference. It is a privilege for me. And I would like to present an application of the wavelet, discrete wavelet transform to damage, localization of damage generally in engineering structures. It is only a part of the project connected to an application of wavelet transform to many problems, but maybe it seems to be an academic problem. But please, I am usually I am also pre-stressed always before my presentation. Oops. It works. Excuse me. Pardon, Marcin.
This is the Prestress from
Okay, not this.
presentation.
Yes, thank you very much. And this is outline of my presentation. What is the damage? Can we define the damage and real basis of wavelet transformation, and generally damage detection, how to do it here in truss structures, and very simple conclusions. And what is damage? It is cracks, voids, inclusions, delaminations, and for example, stiffness reduction, and here the damage will be imposed by the stiffness reduction. And what we should do? Generally, here we should resolve this structure. Resolve, it means to solve the static problem of flat truss structures. And for example, the input signal will be the line of the deflection, but the line of the deflection, for example, the lower chord or the upper chord, or for example, any signal can be here. But then the most engineering signal is, for example, the line of deflection, but it is in discrete form. And here we have a comparison between the continuous Fourier transform versus to the continuous wavelet transform. And a friend of mine, one of the author, Dr. Piątkowska, prepared the monograph about wavelet transforms. There is much more than here. And this general basis and assumption about the wavelet, how to produce the wavelet family. But here we will use the discrete approach. And also here we have two pictures, left the Fourier transform and the right the wavelet transform. And to obtain the wavelet family using the discrete approach, we can substitute A equal 1 divided by the power j and B like here, yes, and we will obtain the wavelet family. And this is an example of the simplest wavelet family. It's the most useful in our analysis that the Debye is 4 and or Debye is 8 wavelet family. Also, the very useful is the family of which is called coiflet. And one of the main point of this analysis is the Malat pyramid algorithm. Yes, we can. This is how to say. Take this part very interesting for us, which really indicate the part of the structure with reduction, which with stiffness reduction, because it is I said that it's a little bit academic problem because we impose this stiffness reduction using our computational approach. But here is the real structure. It is a real structure which was constructed. Now it is, my colleague has calculated using the robot system. And here we have part of this. For example, we can reduce one cross section, reduce the field of the area of the cross section, and the other parametric of this cross section, the moments of inertia, for example. And here this part is indicated using color blue. And to resolve the statics of this, the classical computational program of the finite element method robot was used, and the spatial two-node spatial elements, spatial frame elements were imposed. And here we have the properties of our construction of our structure. And next we have real loading, and this is a part. It was a part of this analysis was a part of a real process of designing of the structure, and we use it to, for example, this part, and to prognose, for example, some weakness inside the structure. and this is real external loading. And now we can now observe how this damage, this reduction of stiffness was introduced. Here we have the results, and the example one is the response signal. It is the deflection of the lower chord. Here should be 128. Pardon, this is only here, but generally the number of measurement was 128. And and we can say that if we have one damage, we can call it damage, yes. And it's quite good localization using this wavelet transformation. And the next example, this diagonals were with the stiffness reduction, and first approach the results. Let's see how we were analyzing the line of deflection of the lower chord. Yes, and this is the results. If it is good, it is under discussion, of course, but we can assume that this damage inside the diagonals also is visible after transformation if we can transform the signal of the deflection of the lower chord. And now, for example, the last, if we measure the nodes of the diagonals, and it is, of course, we can discuss if it is real good results, but generally we can impose after discussion that this two set of family of wavelets indicate this damaged part of the structure. And at the end, some conclusions. Of course, the input signal, it is the response of the structure, can be any signal. It would be, for example, not only the line of deflection in discrete form, but of course the angle of rotation is stress, strain. It can be any signal, but of course there is a main question: what is the most engineering signal in a real structure? Which signal we can measure? Yes, and that's why I said that here is a little bit academic problem. But thank you that your attention, and thank you that I can present our results. Thank you. I can say that my first lecture about wavelets was the lecture of Professor Kamiński during the ECCM 2001, and I was assistant and was on your lecture. Thank you.
Thank you very much. I totally forgot this lecture. Nevertheless, my comment, maybe you have some questions, but before this, I would like to say some comment. There was abbreviation MRA. MRA is multi-resolutional analysis that is very important in multi-scale modeling. There's a lot of paper in the literature about multi-scality and multi-scale analysis using finite element method. In multi-scale approach, there is a huge number of finite elements. Everything must be very carefully discretized. If you use MRA approach, so with wavelet analysis, it is not necessary to provide such a detailed discretization. So that is much better. Daubechy's is after Swedish mathematician Ingrid Daubechy's. She is somewhere in the United States. I don't know where, but in wavelet analysis theory and description, there are some pictures where wavelet analysis is used to smoothen and to make some edges very, very sharp. So to process the pictures, that is very important. If you have any further questions to the author. If not, thank you very much. This session is closed. I invite you once more to the coffee break. A lot of coffee during this conference. Nevertheless, all people are very active. And thank you very much.